A good way to understand a database is to look at the right path and see how data makes it into the system. So we're going to take a tour of Fireproof, starting in the browser, through the cloud, and back to the browser again. When an update occurs in your system, it starts out, of course, in your JavaScript UI code, and it turns into a write to the database, which puts it into the CRDT, the conflict-free replicated data type. This is a data structure designed to never lose updates, specifically concurrent updates, because when two updates happen at the same time, they can be accommodated by recording them both as having the same parent. And then those update streams can go on independently as long as you'd like, continue to fork, and be merged again by an update that counts more than one update as its parent. CRDTs are extremely powerful and useful when you're doing offline or databases that prioritize availability. So our CRDT uses IPLD and IPFS blocks, and because of that, everything that happens in the data structure is written to these immutable blocks. There's also an indexer in Fireproof that creates hash-consistent IPLD trees based on the CRDT data structure. So the big picture here is that you've got updates that come in and they're given a consistent ordering by the CRDT that's going to be the same across all clients. And those updates are played into an index, which is going to look the same no matter what order it's built in. So this allows us to not sweat the details about the size of the epoch that each client applies updates to the index in or anything like that. They just put the content in and everyone will get the same reference to an IPLD block that refers to the indexed data below it. So it all plays nicely with immutable data and content addresses. So what happens to these blocks as they're written? Well, after each transaction completes, it's wrapped up into a car file. And so you can see here a representation of a stream of car files, and they've all got a series of blocks in them, and each one corresponds to a transaction. The first block in the car file is the header, and you're probably familiar with doing this in other car-based data structures. But what this one does in our case is point to the other car files that you need to load in order to run the database. So let's take a look at that. Each car file, of course, can be one transaction, or we can group a bunch of car files together using compaction to make an accelerated loader so you can grab the whole database in just one or two requests. So this is what one of those car files looks like. It's got the IPLD header, and then it's just chock full of blocks, as many as will fit. So we're going to think about the header right now. In the header, there is a list of links to all the car files that you need to get the complete data set, going back to what's either the first car file or the car file that's the result of a compaction. And so this list grows with each operation and each transaction, but is periodically reset when the database is compacted to a single file. And the blue line around this car file is meant to remind us that it's encrypted. So the database, while it does put these car files into IPFS, which we'll see in a second, it doesn't expect the IPFS host to break them open and share the individual blocks within them. That's why it's got to load all the car files from the car log so that then it can decrypt them and serve the blocks from the local browser-powered IPFS instance. So here's a representation of that car log and how it works. There's a write-ahead log stored locally on the client, whether that's the browser or running a Node.js script, that knows how far you've gotten as far as uploading new car files to the cloud. And so you can see in this picture, every car file that's older than the current pointer has been uploaded to the cloud. Now, after a batch of car files has been uploaded and confirmed available, then we can point to the header that tells the client when it comes along later what the current state of the database is. And here we have another CRDT. This is a network available version of the same pale clock that we start with for the database updates from the UI. But instead of tracking the individual updates, this is tracking the car files and the transactions. So you could see here some visualization. This is from a real life clock. In this case, oldest is at the bottom to newest. And here's a zoom in on the same thing that we saw at the beginning of the presentation, where in this case, you could see a stream of updates preceded, and in parallel, another update was written. And then this last update here was done based on both of these, and so it resolves the merge. So that's what it looks like to get the data into Fireproof. And then reading it out is the same as asking the clock what the current situation is, which, it can be something like that. Both of these come back. Loading both of these metadatas out of IPFS, and then applying the internal logical transactions to your existing tree, which might start out empty if it's a fresh load. But all these CRDT applications are idempotent, so you can repeat them over and over again safely, and it allows us to just merge data in when we find it and still guarantee the behavior that developers are expecting from the database. So if you want to run a tiny little IPFS and 500 kilobytes of JavaScript that just keeps car files around in the browser and ships them out to key value storage when it needs it, and program against it using a React-friendly JavaScript API, well, this is your chance. So thanks for watching.